Hi, welcome back. In this lecture I would like to give an introduction to the method of moments. So far the course has been looking at the solution of the Maxwell equation in differential form. So we've seen the finite difference scheme that started from discretizing the derivative. So we start from the Maxwell equation using the formulation using derivatives, and then we discretize the derivative. In the last module, previously to this one, we look at the finite element and methods that also start from a formulation of Maxwell equation in differential form. But then we use this initial differential form to derive a weak form, and then we solve the weak form as a series of equations. So in these modules, the Maxwell equations are reformulated as integral equations. In particular, the field solution is expressed in terms of superposition integrals. So we will have a solution that is several terms, each one is an integral. And each integral involves the sources and a so-called green function that you might have or might not have seen before. So we are looking at the method of moments that in other community also is called boundary element method. So the electromagnetic community normally refers to the integral formulation and the solution of the integral formulation of the Maxwell equation as the method of moments, or MOM. So in applied mathematics, the MOM is often referred to as a boundary element method, also called BEM. We are going to apply the method of moments to these two particular problem. In particular, we're going to focus on the first one, that is the electrostatic problem. So what you're going to do is to reformulate electrostatic equation, the Poisson equation, in integral form. And then we are going to solve the Poisson equation electrostatic system using the method of moments. The major difference is that we will start from integral equation. A second important application is to solve the full Maxwell equation, but in integral equation for the currents on the surfaces of the conductor. And then we apply to a scattering problem. So we have an incident wave on for instance, a thin wire that has been scattered. So that's a second application. So let's look at the first one, that is the integral formulation of electrostatic. As we know, in electrostatic, electric potential phi is determined from the sources according to the Poisson equation. So on the right part of this slide, you see the Poisson equation that is in differential equation, because here we have a nabla that is a second order derivative in space. The Poisson equation tells us that the Laplacian of phi is equal to minus basically the source, that is the charge density. So what we are looking at in this lecture, in this module, is a solution using the integral form. So the solution of Poisson equation in free space can be constructed by superposing. That means that by adding up the contribution of different phi that are q over pi epsilon naught divided on the distance from a certain point r prime. So what we're going to do is we're going to calculate we're going to have this integral equation when phi is basically can be seen as many contribution of a single charge q divided by 4 pi over epsilon 0 still divided by the distance to the charge. And then we can add it up, all these different contribution from a charge from in different places. So the distribution of the charge is given by this rho, that is the charge density distribution. So we can basically sum it up, many contribution coming, we know what is the contribution on the potential from one charge. We can use the superposition principle and calculate the potential, summing up all the contribution from the different charges by solving this integral. We will see that this part here, this 1 over 4 pi epsilon naught, and the distance is what is called the green function for this particular problem. So how we derive that? Well, so if the potential phi is known, can be seen an integral equation for the charge density rho. All right, so we can solve this equation in rho. So we know phi, and when by solving this integral equation we can derive rho. And that's what we are going to do with the method of moments. We're going to find the formulation for rho. The integral formulation is well suited for problems such as capacitance calculation, where the potential is known and conducting boundaries, and charge can occur only on these boundaries. So for instance, if we have a capacitors, we know the charge on the two plates, right? And we can use the method of moments to derive the charge density on the plate. So in the particular problem of the capacitance, the potential is given on the boundary. So for instance, we have a specific 5 that is equal to 0 to one of the plate, and then we have another conductor that is the potential is equal to 1. So we have a difference of potential. Method of moments allow us to calculate the charge rho s on the conducting walls S by solving the integral equation on this slide. So we can look at the formulation for the 2D capacitor problem, where we have two plate for the 2D. So the two plate will be two lines. In the 2D capacitor problem, the surface integral reduces to a line integral, right? So we will have two line integrals for the two plate, and we will use we use the potential from a line charge, in this case minus rho divided 2 pi epsilon naught logarithm of the distance as a weighting of our integral. We will see that later on. This is also the green function of the problem. So we know this expression from previous studies on electromagnetics, so don't worry. This is something that is given. So we are going to apply our method of moments to solve this equation and find a solution basically for rho. So this is a quite well-known expression from electrostatic. In the next lecture, we will provide a more formal framework to derive this expression here, that is called also the green function. So what are the advantages of MOM? Well, the major advantage is the possibility of modeling open geometry, so where there is no fixed boundary condition. In the first in the module for the finite difference and the finite element, we have been looking at the closed system, where we have a system and then we impose a boundary condition on some surfaces or some line. So an example of a closed system is the capacitor that is enclosed in a conducting box. In this case, we saw that the differential equation solvers such as finite difference and FEM work very well, allow us to impose boundary condition on this boundary and solve the equation. So the MOM is very well suited to solve electromagnetics problem in open system. So for instance, where there is no surrounding boss around our capacitor. So we can calculate what is the potential in the free space around the capacitor. In fact, the finite difference and FEM methods have difficulties when truncating the open computational region. So if you use FEM or FD, we basically need to truncate our domain here, and we need to impose the so-called open boundary condition to emulate open system. So with the MOM, we do not have this problem. In fact, the open geometry simplifies the MOM's calculation because it reduces the numbers of surfaces on which the charge can reside. So in this particular case, the charge will be only on the plate of our capacitor. So, and then we're going to calculate what is the contribution of these sources that is distributed on the line of the plate of the capacitor. So this was the last slides. In the next lecture, we are going to look at Green's function and also how to formulate the method of moments to solve the integral equation. Talk to you soon.